5.3 and 4, we are learning about something called monotonicity, and we are revisiting local extrema, which we started on a couple of sections ago. Okay, so once again, we're looking at function analysis. We are drawing conclusions and justifying our conclusions about the behavior of a function based on what the derivative tells us. Okay, so let's start with definition here. We have a differentiable function, okay, on some interval I. So increasing and decreasing are terms that we have heard before. All right. We have a general understanding. Increasing means that it's going up as we move from left to right. Decreasing means it's going down as we move from left to right. But we need to be a little bit more precise than that. Okay. And so f is going to be increasing on an interval if for every pair of numbers x1 and x2 in the interval, if x1 is less than x2, meaning x1 is the point that's to the left, okay, and x2 is the one that's to the right. If that is true, if the point on the left is x1, point on the right is x2, I'm sorry, x1, x2, then f of x1 has to be less than f of x2. In other words, if the point on the left is lower, then the function is increasing over that interval. And this is for any pair of numbers. So that means that, over this interval for any two points that I pick, no matter how close or how far away they are, if the point on the left is less than the point on the right, then the function is increasing over that interval. Likewise, the function is decreasing if for every pair of numbers, the one on the left is higher than the one on the right, okay? What's important here is that increasing and decreasing is defined by the relationship between a point and the points that are on either side of it, okay? So not just what is happening at the point, but is the point higher than the point to the left? Is it lower than the point to the right? Then it is increasing, okay? Or vice versa. And then if we have an interval or a function where where the function is strictly increasing or decreasing, then we say that it is monotonic. This is not a super important word. It's not going to show up on an AP test, but just in the same way that extrema means max or min, monotonic means increasing or decreasing. It's just the word that we use to put both of those together. Okay. So for example, a parabola, not monotonic because it decreases and it increases. Okay. Y equals x, that's monotonic. It is strictly increasing. Now, if a function is not monotonic, we can use calculus to figure out the monotonic intervals, meaning we can find the intervals where the function is increasing and where it is decreasing. So like on the graph of y equals x squared, it's decreasing from negative infinity to 0. It's increasing from 0 to infinity, but we want to have a calculus way to get to that without looking at a graph, okay? So our process is going to be the same as how we start with finding extrema, absolute extrema. We are going to start by finding critical points, okay? And critical points means what? All right, I know you said that this is when f prime equals 0 or does not exist, okay? And then once we have those critical points, we are going to test the sign of the first derivative around those points, okay? If the derivative is positive on an interval, not just at a point, but on an interval, that means that the function is increasing on the interval. So this is where f prime is positive. And if the function is decreasing, then on an interval, that means that the derivative is negative on that interval. So f prime is negative. Okay. Testing the sign. Do you remember back in chapter 0 when we did a bunch of practice with solving nonlinear inequalities? This is why we did this, because we're going to do a lot of testing the signs for nonlinear functions where we find our critical points by setting an expression equal to 0 and then and solving, and then we need to do test points around that. So remember, with nonlinear inequalities, you have to do test points on the number line, and we're going to call those sign charts. Okay, so we'll see here in a second. We're gonna come back to A. We're gonna start on B. All right, so B is a cubic function. Make that a little bit bigger. B is a cubic function. We know that it has a leading coefficient that's positive, so it probably looks something like this. Just to give us a rough idea of what we're looking for. Okay, we should be looking for something that starts by increasing and then it decreases and then it increases. Okay, so let's see if we figure that out with our process here. We start by finding the critical point, so that's the derivative, 3x squared minus 6x minus 9. We are going to set this equal to 0. There's nowhere that it doesn't exist. I'm going to divide everything by 3. So I have x squared minus 2x minus 3 equals 0. And then I'm factoring to solve So I get x equals 3 and negative 1. Okay, those are my critical points. Now I am going to come and I'm going to draw a number line. Please make sure you put the smaller number on the left. And then I'm going to test the sign of the derivative around these points, okay? Pro tip, when you're finding the sign of the derivative, if there is a factored form of the derivative, this is the easiest one to test the sign. I could, like, if I could take -2 and I could plug it into this equation, but that takes a lot more computation when all I really care about is, do we have a positive or negative number? Whereas if I just take a number to the left of -1, I can say, okay, this factor is negative, this factor is negative, negative times negative is positive, and I don't even really care what that number is. Okay, so this is just kind of some efficiency for algebra suggestions. You don't have to take them if you don't want to, but just trying to make your life a little easier. Okay, also, if we have a linear factor like this x plus 1, as I move from the left to the right of that on the number line, this factor will change signs. So then I have negative times a positive, which is negative. Or again, if that doesn't make sense, then just say, okay, I'm going to plug a number like 0 in here and I get -3 times +1, which is -3, okay? However you need to do it, just get the sign of the derivative at each of these places. When I go to the right of 3, now this one changes signs, so we have positive, positive. Okay, so this sign chart, it is worth noting here, the sign chart does not count as showing work. You will have to justify these types of problems on an AP test. The sign chart, the readers don't even look at, okay? They pretend like that's scratch work and they completely ignore it. So it doesn't work for a justification, but it is our process for getting to our conclusions, okay? So because I have a positive derivative on these two intervals, I'm gonna say that f is increasing on negative infinity to -1 and on, I'm gonna come over here actually, and on 3 to infinity. It doesn't tell me to justify in this question, but we might as well get in the habit of doing that. And I'm going to say, because f prime is positive, and that is a perfect justification for an increasing interval. Also, no, I don't care if you use a union symbol or a comma or the word and or, the word or, doesn't matter, okay? And then I'm going to say f is decreasing on the interval from -1 to 3, because f prime is less than 0 or negative, okay? So there's complete work. We did the test points on the number line, but the sign chart does not count for, part of our justification. And we have a statement that uses the derivative to indicate where we have increasing and decreasing intervals. Okay, it is worth noting here also that the endpoints of the intervals for increasing and decreasing can be open or closed as long as an endpoint exists. Now, if there's an asymptote or it goes to infinity, obviously you need to use an open interval. But here I could say from -infinity to -1 and put a bracket here, and that would be totally fine. Or I can use, and same thing over here on the 3, or I can use the parentheses. Now, I would strongly recommend that you use parentheses. This is the way that I do it. The reason I do this is because even though intervals of increasing and decreasing could include the endpoints, or so they could be open or closed, intervals of concavity have to be open. And so that I don't accidentally write intervals of concavity with closed intervals, I just always get in the habit of writing them as open intervals, okay? All right, let's come back to this previous one, and we'll talk a little bit more about the endpoints here. Okay, so we know what the graph of this looks like, okay? Looks something kind of like that. If I take my derivative to find critical points, I get 3x squared. I set this equal to 0. I get x equals 0, okay? If I do a test points on the number line here, I have a positive derivative on both sides of 3 for 3x squared. I have a positive derivative. Okay, so you might say, all right, well, that means that it's increasing. Move that back. That means it is increasing from -infinity to 0 and from 0 to infinity. But the question is, what's happening at 0? Okay, and this is important. When I said that 0 could be included or not included, this is one of the reasons that we need to consider that it can be included. Our definition for increasing said, for any two numbers, if the number on the left is less than the number on the right, then the function is increasing. Okay, so if I think about what's happening at 0, I didn't really put axes on here, but if I think about what's happening at 0, f of 0 is higher than any point that's to the left of it, and it is lower than any point that is to the right of it. So really, this function is increasing everywhere. Okay, meaning I have to include the 0. All right, if I were to write this as my answer and leave out the 0, it would be marked wrong because the function does increase all the way through an interval that includes 0. Okay, so let me stress this again. It doesn't matter what is happening at the point. Okay, yes, a positive derivative means the function is increasing, if it's on an interval, but at the point, it doesn't matter if the derivative is equal to 0 as long as it is higher than a point to the left or lower than a point to the right, then the function is increasing through the interval containing that point. Okay, so yes, this one is increasing everywhere. It doesn't matter that the derivative equals 0 at 0. Okay, I'm going to stop here and pick up with the rest of this section in the next video.